Good morning. The subject of the lecture is mathematical induction. What is mathematical induction? According to Wikipedia, mathematical induction is a mathematical proof technique used to prove a given statement about any well-ordered set. Most commonly, it is used to establish statements for the set of all natural numbers. Mathematical induction is a form of a direct proof, usually done in two steps. When trying to prove a given statement for a set of natural numbers, the first step, known as the base case, is to prove the to prove the given statement for the first natural number, or number 1, n equals 1 is the base case. Okay, we will prove that the statement is true for n equals 1. This is the this is the this is the this is the first steps. It is called the base case. And the second step, that is known as the inductive step, is to prove that if the statement is assumed to be true for any one natural number, then it must be true for the next natural number as well. For example, if the statement is true for n, then it is true also for n plus 1. Having proved these two steps of the rule of inference establishes the statement to be true for all natural numbers. Okay? When we assume that the statement is true for n, and then we proved it that the statement is true for n plus 1, my assumption is the statement is true for n, and I will prove it for n plus 1. Okay? My assumption, I must assume that the statement is true for n. This is my assumption. And according to my assumption, I will prove that the statement is also true for n plus 1. Okay? Okay, I rely on the assumption that the statement is true for n. N is any natural number, and then I proved it. I will prove it, okay, according to my assumption that the statement is also true for n plus 1. N plus 1. Okay? We have also metaphors that used to understand the concept of mathematical induction, such as the following one. Mathematical induction proves that we can climb as high as we like on a ladder by proving that we can climb onto the bottom rung, and that from each rung we can climb up to the next one. That is the induction. The basis of this metaphor, the basis is that we can climb onto the bottom rung. Yes, that is the first step, the base case, and then we proved that we can climb up to the next one. That we can climb from each rung to the next one. That is the second step, that is called the inductive step. Okay? Now, okay, I will give an example to understand more what is mathematical induction. We have the general equation that 1 plus 2 plus 3 plus 4 plus n equals to n multiplied by n plus 1 divided by 2. That is the equation that needed to be proved, and we prove it by induction, by mathematical induction. Suppose that you see the equation. Okay, 1 plus 2 plus 3 plus 4 plus 5 plus n equals to n multiplied by n plus 1 and all divided by 2. Okay, the first step is the base case that we will check if this equation is true for n equals to 1. If n equals to 1, now we are in the first step, that is the base case. If n equals to 1, then in the left side of the equation we have only the number 1. It says that 1 equals to n that equals to 1 multiplied by n plus 1, that is 2, n multiplied by 2 is 2, and 2 divided by 2 is 1. Okay, we get that the left side of the equation equals to the right side of this equation, i.e. that 1 equals to 1. Okay, we finished the first step of the mathematical induction, that is the base case. Now we will go to the next steps, that is the inductive step. We need to prove that 1 plus 2 plus 3 plus 4 plus 5 plus 6, etc. equals to n multiplied by n plus 1, and all is divided by 2. Okay. Excuse me. Now the inductive step will be that we assume that this equation is true. That is our assumption, that this equation is true, and when we rely on the assumption that this equation is true, we will prove that the equation also true for n plus 1. So my assumption is that 1 plus 2 plus 3 plus 5 plus etc. plus etc. equals to n multiplied by n plus 1, and all is divided by 2. This is our assumption, and when we rely on this assumption, we will prove that 1 plus 2 plus 3 plus etc. plus n plus 1 equals to n plus 1 multiplied by n plus 2, and all is divided by 2. Okay. The first equation is assumed to be true by that is our assumption, and the second equation is what we need to be proved according to the first equation. Okay, now we will write down this the second equation in this manner. The second equation, the left side of the second equation is 1 plus 2 plus 3 plus 4 plus etc. n plus n plus 1 is equals to what? 1 plus 2 plus 1. Okay, here we put brackets. Here we put brackets. Here we put brackets between 1 plus 2 plus 3 etc. plus n is my assumption that is true, and then n plus 1 is like this, n plus 1. But we know that according to our assumption, 1 plus 2 plus 3 plus 4 plus n is equals to n multiplied by n plus 1, and all is divided by 2. Okay, that is our assumption, that the first equation is true. So we can change, or we can change the left side of equation 1 by the right side of equation 1, because the right side of the equation is equals to the left side of the equation. According to our assumption, the first equation is true. So what we did here is change the left side of equation 1 by the right side of equation 1. So in place of 1 of 2, instead of 1 of 2 and 1 plus 2 plus 3 plus etc. plus n, we write n multiplied by n plus 1, and all is divided by 2. It is allowed to do so because the two sides of the equation are equal. Okay, so instead of 1 plus 2 plus n, we write down n, we write n multiplied by n plus 1 and all divided by 2. Left side of equation 1 equals to the right side of equation 1, and all we did is to replace the left side of the equation with the right side of the equation. Okay, and what we left is with n plus 1. So we also write n plus 1, and all of this is equals to, if we multiply, if we open the brackets, then n, if we open these brackets, is we get that it is n square plus n. Okay, we opened these brackets, and then if we put n plus 1 on there, then we get that we multiply by 2 and we divide by 2, so we didn't change anything. So we get there 2n plus 2, all is divided by 2. Okay, and then it is very simple to get the last pairs, that n square plus n. If we get n outside, we can get n, and in the brackets we can get n plus 1, and then if we take 2 outside, then we get the 2n plus 2 is 2 brackets n plus 1, and then we have in total n plus 1 multiplied by n plus 2, and all is divided by 2. So we proved that the equation 2 is also true. We relied on the assumption the equation 1 is true, and according to our assumption that equation 1 is true, we proved that equation 2 is also true. This is equation 1, this is equation 2. We relied on the assumption that equation 1 is true, and according to our assumptions, we proved that that the equation 2 is also true. So what we did is that we assumed that our that is true for n, and according to our assumption that it is true for n, we proved it for n plus 1. So that is all the example. Also, okay, I hope that you understand it. So we proved by mathematical induction that 1 plus 2 plus 3 plus 4 plus n is equal to n multiplied by n plus 1, and all is divided by 2. Okay, that is what we proved there. We proved that this equation is true according to the mathematical induction. So I will now repeat on the subject of mathematical induction. Okay, so mathematical induction is a mathematical proof technique used to prove a given statement about well-ordered set. We assume that the statement is true for n, and according to our assumption, we will prove that it is true for n plus 1. The first step is the base case, that we check if our statement is true for n equals to 1. Okay, this is the first step. It is called the base case. we take the equation, we put in this equation n equals to 1, and we should check if the equation is true. Okay, this is the first step that is called the base case, and then the second step that is called the inductive step is to assume that the statement is true for n, and according to our assumption that the statement is true for n, we need to prove it that this statement is also true for n plus 1. This is the definition of mathematical induction, and we also proved that the the statement that the equation that says that 1 plus 2 plus 3 plus 4 plus etc. plus n is equals to n multiplied by n plus 1 and all divided by 2 is true for all the natural numbers. This is our argument. The first step, we check if this statement, okay, in the first step we check if this statement that you see there is true for n equals to 1, and we see that for n equals to 1, the left side of the equation is equals to the right side of the equation. 1 equals to 1 because n equals to 1. When you checked it, we can check also for n equals to 2, but it's not necessary. It is sufficient to check only for n equals to 1. So we checked our statement if it's true for n equals to 1. This is the first step that is called the base case, and then when we pass the first step of the mathematical induction, then we go to the second step, that is the inductive step. What is the inductive step? We assume that this equation that you see is true for n, for natural n. This is our assumption. This is the mathematical induction's assumption, that this statement is true for natural n, and according to our assumption we need to prove that this statement is also true for n plus 1. That is the inductive step. Also, okay, we saw also that you see there that we have already proved that if we assume that this equation is true, so it is true for n, then we have already proved that is true also for n plus 1. That is the meaning of that it is true for n plus 1, that we add n and also n plus 1. That is the meaning of the equation. How we do it? We substitute this. With this. This equals to this. 1 plus 2 plus 3 plus n is equals to n multiplied by n plus 1, and all is divided by 2. So we substitute, we change, instead of this, the left side of the equation, we wrote the right side of the equation there. We can do it because our assumption is that that equation is true. That is our assumption. We need to prove that the second equation is true. So we can change this 1 plus 2 plus n with the right side of the equation that is assumed to be true. We change it and we get that the left side of equation 2 is equal to the right side of equation 2. So that is the way that we proved that the second equation is also true. We proved it according to our assumption that the first equation is true. According to our assumption that our statement is true for n, we proved it that is true also for n plus 1. So that was our example. And what we did in the first step, we checked that our statement is true for n equals to 1. We put instead of n 1, and we saw that the left side of the equation equals to the right side of the equation. 1 equals to 1. We checked it by putting n equals to 1 in the equation that is to be proven that is true. Then we assumed that our equation is true for natural number n, and according to our assumption that is true for natural number n, we proved that is also true for n plus 1. That is exactly what we did. We proved the second equation that our statement is also true for n plus 1, and that is the way that we proved that is true for all the natural numbers. Why? Because if it is true for n equals to 1, then it's true for n equals for n plus 1. N plus 1 is 2. But if it is true for 2, it is also true for 3. And it is true for 3, it also true for 4, because we generally prove that if it's true for n, it can be any natural number that we choose, it's also true for n plus 1. That is what we proved, we also proved. So if it is true for 1, it's true for 2. If it is true for 2, it's true for 3. If it is true for 3, it is true for 5, etc., etc., etc. So we proved that our statement is true for all the natural numbers, and that what we needed to be proved, that our statement is true for all the natural numbers. So we checked for n equals to 1, and then we generally prove that if it is true for n, it is also true for n plus 1, and that is what we need to prove by mathematical induction, that the statement is true for all the natural numbers. Okay, so if we repeat again, I tell that mathematical induction is a method to prove that a statement is true for all the natural numbers, and we have two steps. The first step is the base case, that we prove that the statement, we check that the statement is true for n equals to 1. Then if it is true for n equals to 1, then the next step is to prove that our statement, we need to prove, we assume that our statement is true for n that can be any natural number, and according to our assumption that our statement is true for n, we prove it that is also true for n plus 1. If we pass those two steps, then we proved, according to mathematical induction, that our statement is true for all the natural numbers. Okay, so we conclude that mathematical induction is a mathematical proof technique used to prove that a given statement is true about any well-ordered set, and is true for all the natural numbers. In Wikipedia it is said that it is a mathematical proof technique. It is a mathematical proof technique used to prove that a given statement is true about a well-ordered set. But what is usually a well-ordered, when we say a well-ordered set, usually we mean the natural numbers. So I explained it about the natural numbers, that we assumed that the statement is true for n equals to 1. This is the first step, that is called the base case. If we pass the first step, then we can go to the next step. This is the inductive step. In the inductive step, we assume that our statement is true for n, that is any natural number, and according to our assumption that is true for n, we prove it for n plus 1. Then we proved that our statement is true for all the natural numbers. Why? Because if it is true for 1, it's true also for 1 plus 1, that is 2. If it is true for 2, it is also true for 2 plus 1, that is 3. If it is true for 3, it is also true for 3 plus 1, that is 4, etc., etc., etc. Okay, so in this way we prove that it is true for all the natural numbers. Okay, I hope that you enjoy my lecture. Okay, thank you, see you later, goodbye.